Good morning, everyone. This is the first session, so we welcome Mairi Sakellariadou from King's College in London, who is going to talk to us about cosmology in the era of gravitational-waves astrophysics.
So good morning, and let me thank the organizers for the invitation to this meeting. So I would like indeed to talk about cosmology in the era of gravitational-wave astrophysics. Okay, so as we heard and as we all know, the standard model that we all use in cosmology, we like it or not, is the lambda CDM model, which is a phenomenological model based on Einstein's theory of general relativity with some ingredients put by hand, the cold dark matter, the dark energy, and also a period of exponential expansion, which we call inflation. So I will go one by one to these ingredients, say how robust they are, what alternatives exist, how we can make some tests with this kind of ingredients with gravitational waves. Okay, so I started with the general relativity. As you know, it has passed all tests. The ultimate test was the detection of gravitational waves, which, I just give the first detection a few years back, and by now we have public around 90 events, but we'll have a few more tens that soon would probably be completely public. So this goes the test of GR, the ultimate test of the GR. However, we do know that at some point, general relativity is going to break down. When we go to very high energy scales, then we do know that at that point, quantum gravity corrections can by no longer be neglected. And there is a plethora of models that attempt to somehow answer this question and propose a theory of quantum gravity. Here you have all the zoo of the proposals which exist: ADS-CFT, asymptotically shaped gravity, causal sets, dynamical triangulations, group field theory, loop quantum gravity and spin forms, matrix attention models, non-commutative geometry, or string theory. Any of them could be correct, partially correct, or completely wrong. Now, the next ingredient which exists is putting by hand the cold dark matter. And there is quite some evidence about the need for cold dark matter, flat rotation curves and the bullet cluster, the cosmic microwave background radiation. So there have been various proposals what this cold dark matter could be. Primordial black holes and axion-like particles are the ones which are a bit more fashionable today. In the past, of course, people thought the light is supersymmetric particle. Supersymmetry has not been found. This kind of proposal has been a bit abandoned. So let me discuss a bit about the primordial black holes and the axion-like particles, why we like, what exists there. And then in the second part of the talk, it will be short, don't worry, then I will discuss how we can put some constraints from gravitational waves. So why people like primordial black holes? Because there is a very large number of mechanisms that can lead to the production of primordial black holes. Collapse of primordial density fluctuations. If you accept an inflationary scenario, then collapse of inflationary fluctuations. Collapse at the QCD phase transitions. It could be cosmic strings either at the cusp of a string or the loop altogether, that they can collapse and create primordial black holes. Collapse through collisions of bubbles of a broken symmetry at the spontaneous symmetry breaking phase, the collapse of a scalar field or domain walls. And they may be even more, but that's a whole list of various mechanisms that can lead to the formation of primordial black holes. And the interest with primordial black holes is that they span a very large range of masses, because they could, when they were formed, they could have a mass which corresponds at the horizon at that time. And you know that with the Hawking radiation, primordial black holes evaporate. So usually people express the energy density, the fraction of the dark matter in primordial black holes, this quantity F, which is the energy density of primordial black holes, normalized by the critical energy density with respect to the energy density of cold dark matter. And there are constraints on what kind of fraction of primordial black holes could be as a dark matter. Depending on their mass, you have three ranges: asteroidal to sublunar range, intermediate range between 10 and 100 solar masses, and extremely large range of primordial black holes, which, however, are not interesting for dark matter. And they gain a lot of interest because the detection of LIGO-Virgo-Kagra collaboration of black holes at the range between 10 and 50 solar masses, which is exactly this intermediate range of primordial black holes. And there was a lot of interest whether what we have detected with LIGO could be a primordial black hole or not. Of course, if you do find a black hole of subsolar mass, then you know by default that is primordial because there is no mechanism that can lead to a primordial black hole, to an astrophysical black hole of that kind of mass. And then there is a variety. If you go beyond the standard model of particle physics, then you could have massive bosons which are beyond the Higgs, beyond the ones which we don't know, like the W and the Z, and depends whether you want to have a vector particle, pseudoscalar. There are possible candidates for dark matter, and the axion particle, which has been introduced to solve the QCD kind of problem and the Peccei-Quinn symmetry breaking, that could be a possible candidate for dark matter. Now, let me then proceed. There has been some other attempts that probably there is not a dark matter in terms of a particle, but you need a modification of Newtonian dynamics. That was Mond, and then was this promoted to a relativistic theory with Teves, tensor vector scalar theory. So Mond just tells you that if you are above below a given kind of threshold, which is set by this parameter A0, the value was set for galactic rotation curves, then you have a modification of Newtonian dynamics. You have this function f, which is monotonic. If this function is equal to its argument, then you have the deep Mondian regime. If it's equal to 1, then you have the standard kind of Newtonian physics. And they have been studied in the literature different kind of forms of expression for this function f. It was pretty successful, not extremely successful, but quite successful to match rotation curves. Of course, it's an empirical law, and then it has been promoted to a relativistic theory. This is the Lagrangian. It is the ugliest kind of model that I have seen, and the less well motivated. Now, as an exercise, several years back, we took this kind of expression. We recalculated the formula for gravitational lensing, and we tried to see if with same kind of, there is one free parameter, this alpha that I gave before, in the most general expression for this f function, if with the same value of this parameter, you can fit both flat rotation curves and gravitational lensing, and the answer was no. So to me, this is a legitimate kind of approach, is a good idea, but I don't think that, at least as it is, it worked. So even if some reasonable candidates exist, still after 90 years from when we know the problem of dark matter, I don't think that we have reached a kind of consensus what this dark matter could be. And then I proceed with the dark energy. So dark energy, again, we do know that it exists. We have data that tell us that we are in an accelerated expansion. It has been confirmed that we need to meet the data of the CMB, provided they are analyzed within the standard kind of canonical cosmological model, and as well from large-scale structure. We have data that support that we should have a kind of dark energy. What could it be that? We heard, I think yesterday, discussion about that as well. It could be a cosmological constant, could be a quiescence, and that has been also, I think, was in one of the talks the other day. It could be failure of general relativity. That means at large scale, somehow gravity is changed, and you could have different models that have been proposed, like massive gravity, degravitation, or if you go a bit more exotic, theories with extra dimensions. And one might also consider that you can have this as a result of back reaction. So the structure formation is going to modify the geometry of your background, and then this is going to imply a kind of modification between the relation that gives you distance and redshift. And then we go to the last kind of problematic stone of this idea is inflation. So you know that inflation, again, as I often say, is a paradigm in search of a theory. Here I give the 3 equivalent definitions of inflation. But despite the number of papers here, I think I was even a bit very conservative to write 14,000. I think there may be many more that somehow they have a title of single inflation. It remains like a mechanism that we know how it works, but we don't know what is behind inflation, what is the origin, in other words, of inflation, what are the initial conditions, how generic initial conditions you can have to lead inflation. That's an exercise that we did in the past, and we found that the initial conditions might not be that generic as one may want to think. And also because at any rate, at the energy scale where inflation took place, then you know by default that you are in a regime that quantum gravity should take into account. And of course, there are very proposals to go beyond that. People go around and say, well, Higgs inflation is the only scalar field we know that exists. Higgs inflation could do the job. It could, provided you somehow tune the coupling of the Higgs. And I'm not sure that this is very, very natural. So here I put the constraint that you need in order to be in agreement with the CMB data. So to me, it is a kind of fine-tuning. There are alternatives to inflation. Bounds, there are many models with bounds, ekpyrotic, pre-Big Bang or string gas theory. These are models which come from fundamental strings and extra dimensions. There is as well, if you wish, the kind of Starobinsky model, so you have higher order corrections. This is fine, provided they have the correct sign, otherwise you have a ghost, and provided you can motivate where does this come from. And up to now, from quantum gravity proposals, we have not seen that indeed there is a way that we can motivate the existence of this extra term. So I think the kind of immediate first order tasks that we have working in cosmology is to understand what is dark matter, what does it provide the late time accelerated expansion, what does it provide the late time accelerated expansion as well. And if we can know what gives the early time accelerated expansion, then we might find what is the initial origin of density fluctuations. We know from gravitational stability, they can create the structures we see. So what is dark matter? As I said before, the 2 plausible candidates today that I know of are primordial black holes and axion-like particles. So I will try to see how we can test this hypothesis with gravitational waves. For the other 2 questions, I believe indeed that it may be the failure of GR, not the failure of GR, but the fact that it's a classical theory that it could be corrections from quantum gravity regime that could show their influence. Now, for the last part, the early time accelerated expansion, when I say failure of GR, which I mean if you take quantum gravity corrections, I give you here the standard kind of action that people take, which is supplemented by a matter component, the matter Lagrangian. And usually what people do, as a matter of fact, I summarize what I wrote here, they take a quantum gravity kind of framework, whatever you want. You try to see how the background equations are going to change. In other words, you have the changes in the Friedmann equation. You have a modified Friedmann equation. And then they put by hand the matter part, and then they see how the inflationary dynamics are going to change if you have that the Friedmann equation will be different because you have a modification from GR. And I don't think that this is the correct kind of approach. I think that the correct approach is that this matter component should come from the theory itself. Otherwise, if you plug the inflationary thing by hand, you don't gain much. You just get a modification, therefore, of the inflationary dynamics, but I don't think that this solves the problem. So there are, therefore, since I said that there are ways that you could do that from quantum gravity, I give you an example of how we try to do that with Marco, who is seated in the back over there. So that was in the context of group field theory, which is one of the approaches to do quantum gravity. Then here you just expect somehow that you have an emergence of your space-time for some discrete pre-geometric quantum structures. So you have like that your quanta of geometry. And in order to somehow specify this theory, you have to choose a filter, which I will call sigma, is a complex scalar field. And you have to choose an axion, which will have a kinetic term. And then you will have some kind of, these interactions, which it is written there. So you have the axion, and you have the potential. And what then we try to see, we wrote down an expression for inflation, even if you do not have a metric. The quantity which I write here, V double dot, V is the fundamental, if you want, volume. The prime is derivative with respect to a scalar field, which plays the role of relational time. So this expression is valid even if you do not have a proper time. We have relational time, even if we do not have a classical space-time. I do not have a metric. I don't have a scale factor. And then here n gives you the number of fivefolds. And what, just to make the long story short, what we have found is that if I have some conditions about these expressions of the polynomial, then I can have as many if-folds as I want, which means that how I glue my quanta of geometry may give me the dynamics that I want for an exponential expansion. So to make the long story short, the message from that is that it could be that the way that I construct my background, whatever you want to call it, in this quantum gravity approach might give me the kind of inflationary, exponential kind of expansion of the early universe. So that's a kind of paradigm, I believe, that this kind of dynamics could emerge from the theory itself without introducing by hand a scalar field with a fine-tuned potential. So there are various models. And then I believe that there is an intimate relation between cosmology and, and any kind of quantum theory of geometry, because it could be quite naive to believe that at any time we'll be able to reach the energy scales we want in order to test in a lab. So, we're going to request a 10 to the 19 GeV, which is completely impossible. But I believe we're very lucky because we live within an experiment that keeps going for about 47 billion light years. And then, it releases tremendous amount of information, and that is our own universe. So what I'm going to do, I'm going to try to test some of these kind of ingredients of the lambda CDM model by using gravitational waves. So there are different ways that you can test how the gravitational waves are generated, which means via changes in the waveform. For instance, that we did it if we have an axion field. Propagation, it will be a modified dispersion relation, and many theories that they go to extending models of gravity, they introduce modified in the dispersion relation. And polarization, and of course as well, what is the remnant, which I will not discuss here. And I will highlight already with one binary neutron star event, we're able to rule out one proposal of extra dimensions that Vali, Kabadadze, I can never pronounce that, and Porati model. Were able to say which models of quantum gravity they could be tested with gravitational waves, provided there is electromagnetic counterpart. And then we were able as well to put constraints in theories which predict that you will have the speed of propagation of gravity that will depend on the frequency. So let me take the first example. So you know that in string theory, there exists as well a possibility of extra dimensions. So you have the bulk within which you can have branes of any dimensionality your theory allows you to have. Gravity propagates everywhere, that's why it is weak, and all the matter fields are on the brane. Now, what it happens is that we have the GW170817, which was a gravitational wave event that was followed by gamma rays 1.7 seconds after the detection of the gravitational waves. And you can make a comparison between the strain, which you read from your interferometer, and the luminosity distance, which you have from the electromagnetic counterpart. The expression goes there. It is for all models where you have this kind of screening mechanism, which is going beyond a certain radius, which I call R with a subscript C, if I'm not wrong. Then you will have that gravitational radiation is going to leak to the extra dimension. And by this just one event, we were able to put constraints on theories as a function of this steepness, which is this n, and this screening radius, which was RC. So one model was ruled out, and then we remained like that. There is agreement, there is consistency with general relativity in 4 dimensions. Now, how you can test theories where predict that you might have modified dispersion relation. The way basically that we do that in the collaboration is by just putting a phenomenological term, which is, well, I cannot make it. This red thing here is a phenomenological parameter which depends on this capital A and alpha. Different values depend on different models of extending gravity, if you wish. And then what you are going to have, there will be a modification in the phase of the gravitational wave. Okay, here you have the strain, n is the frequency, I'm in Fourier space, this is the amplitude, this is phi capital is the phase, so you have this kind of modification. The expressions are given here, I'm not particularly interested. And then what you see, we were able to put constraints from just one event for the values of capital A and small alpha, which means you can go now, do the mapping in your preferred beyond GR theory and see how it is constrained. And in addition, from this kind of discrepancy between the time of arrival of the 2 signals, we could provide the strongest possible existed limit on the mass of the graviton, which is 1.27 times 10 to the minus 23 electron volt. It's about 2 times stronger than the one that you can put from solar system. And by now, we have a couple of more BNS, so probably this may become stronger. There are theories where you expect to have extra polarization terms, okay? So you could have up to 6 polarization terms. Now, the point is how you are going to test them. And in order to test, so 2 plus the 4, 6, you need at least to have 6 interferometers. We have up to now 3. Well, and one is not working very well right now, but anyway, we have 3. And it seems to be that the 2 of them, the 2 LIGO, have the same orientation. So there is no way that we can do that with transient effects. However, we were able to do it by proposing a kind of Bayesian analysis. So you have the omega GW that you see is the energy density of gravitational waves in a logarithmic interval of frequency normalized by the critical energy density. And usually, so this omega, because people thought that the gravitational wave background overall will be from cosmological sources, so it is expressed in everything in cosmology with this dimensional parameter omega. So it has a power law dependence on frequency. The value of this power law depends on what is the source. And then as you can see here, there might be 3 different kinds of powers, because it depends if you have the scalar, the vector, the tensor modes. So what we have done, we did a Bayesian kind of analysis, just giving the same probability to the neo-noise and each of the possible kind of signal by giving the same kind of probability to the 7 hypotheses that you can have, what I have, vector only, tensor only, scalar tensor, or combination of 2 or all the 3 of them. And as well by doing a kind of Bayesian analysis between GR and non-GR, and everything so far that has been used up to the data of the gravitational wave background, up to the 3 observing runs that we have, and we are going to do it with the current. Now, we are in the middle of the second part of the 4th observing run. We see consistency with GR, so we do not see any signal of extra polarization modes. Now, there is another way that if you want to test theories beyond classical kind of GR and quantum gravity, So what we did at some point, we discussed the effect of what is called the dimensional flow, which means that the space-time is going to change depending what is the scale that you probe. So let me consider that I have my space-time to be distorted by some effects of quantum gravity origin, which I'm going to write in terms of a space-time measure ρ and a kinetic term k. So this is the expression that you see the action there, where this gamma is the Hausdorff dimension the expression is given over there, which value I know for different quantum gravity theories. So I can go there and I can see what will be the amplitude of the tensor perturbations, which means gravitational waves. And what we found is that it's going to be the convolution of the source J and a Green's function. And if you go to write it down, you will see that at the end it is the product of, so the amplitude here, it is the product of a quantity which depends on the source and has no dimension and this power law distance behavior. So then you can go and pick up what kind of theory you want. Here I have the whole list. GFT, spin forms, loop quantum gravity, causal dynamical triangulation, Kappa-Minkowski, stellar gravity. You take the whole thing. And you go to read from the literature and find what are these values of gamma. You have theories which have more than one scales. So the scale gamma UV is the scale at which quantum gravity effects are dominant, and gamma mesoscopic is the scale at which the effects cannot be neglected. So then, if you have electromagnetic counterpart, you go again and you can write down an expression that will give you the relation between the strain from the interferometer and the strain that you will get if you read the luminosity distance. And everything will depend on the value of this quantity gamma. So you can put some kind of constraint in the parameters lambda star and gamma by constraining the ratio between the gravitational waves and the electromagnetic luminosity distance. So we injected various data within the capability of LISA, and what we found that the only theories that could be tested with electromagnetic counterpart are the ones that I wrote there, group field theory, spin forms, or loop quantum gravity. Just to emphasize, not to give the wrong impression, I do not say that any of these three theories is the correct one. They might be completely wrong. I'm saying only these three theories can be tested with gravitational waves that have electromagnetic counterpart. Now, there is a variety of theories as well that tells you that the propagation of gravitational waves might depend on frequency. But we have a very strong constraint, which I gave before, from the BNS, GW170817, which means that we cannot be very far from the speed of light. However, there are theories, the whole list that you have there, which tell you that you might have a speed of propagation of gravitational waves, which depends on the frequency. So then I am in the kilohertz range, where LIGO gives me the data, the speed of light, and I could be different in the millihertz, where LISA is going to do that. So here is then two models which we have used, this polynomial ansatz and this EFT-inspired ansatz, which means that I have the propagation of the gravitas that depends on the frequency, and I need to see if, by studying the modification in the strain, and it means the amplitude at the frequency, I will be able to put constraints on this extra free parameter, F star and C0, as well as in the GR parameters. So we did, I'm not going to bother you, but to tell you that we did that. We write post-Newtonian kind of corrections, and we found that we will be able to do this test with LISA. Why I emphasize that? Because here I do not need electromagnetic counterparts. And given from about 120, 150 events we have now, the electromagnetic counterparts was only 3 times, it's good to find a kind of test which does not imply the need for electromagnetic counterpart. Now, I would like to move to the things that I told you about primordial black holes and axions. Okay, yeah. So, as I said, there is a variety of models that can lead to the formation of primordial black holes. The one that has been studied more in the literature is the one where you have gravitational waves to be at the second order in perturbation theory from scalar perturbations. So in that case, the spectrum of the scalar-induced gravitational waves is fixed by the curvature power spectrum, and CMB data put very strong constraints to be about 10 to the minus 7, 10 to the minus 7, 10 to the minus 9, which is extremely weak. There is no way that you can get it. However, if primordial black holes were formed at the radiation-dominated era, then it is sufficient the amplitude of the power spectrum to be about 10 to the minus 2. And then there is within the gravitational waves capabilities, and then it is, there are several inflationary models. We like them or not, but let's play with that. There are several inflationary models which give these peaks in the power spectrum at exactly around 10 to the minus 2. So then what you do is, if you know what is the power spectrum of the primordial curvature perturbation, then you can calculate the power spectrum of the induced gravitational waves. You can plug it here, and you take the omega GW, the energy density of gravitational waves that you have within the universe. So we took a kind of generic form for the curvature power spectrum, which depends on the amplitude, the position, and the width, this A, delta, and K star. And as you can see from these plots, which they give already which area is ruled out, is this reddish area. You can see that with the current LIGO Virgo data, we're already better than BBN and CMB, and as the sensitivity will become better, or 30 detectors will be available, then we can really enlarge the kind of exclusion range. And this you can go and map it. What does it imply for the origin of these primordial black holes? Now, I will go very fast here, but here is the idea what exists, okay? There could be an action field, okay? Now, this action field, if it is within an object which is pretty dense, like a neutron star, then it can get some kind of corrections. And then what it happens is that if you have the radius of these objects to be within a certain kind of range, then you might have a phase transition which brings this action field from the 0 to a non-zero value. The result of this is that if you have actions within two neutron stars, then there's going to be an extra scalar force, okay? It's going to be repulsive or attractive, it depends, and then this is going to modify the waveform of the gravitational waves which are going to receive. So when we studied that at that time, there was no BNS kind of detection, and we said LIGO one day will be able to put constraints in actions with mass smaller than 10 to the minus 11 electrovolt, with this kind of decay rate. And then we were lucky enough, because the BNS was found, and then we were able, by doing post-Newtonian expansion, to find the corrections that you have in the waveform, and then to exclude, like that, actions with masses below 10 to the minus 11 electrovolt, if their decay constant is within these values of 10 to the 16 to 10 to the 18 GeV. So I was able to put constraints in actions. The last first thing that I would like to say here is about the dark matter, the cold dark matter, the idea that exists, that there is cold dark matter. And they might be, warm dark matter, interactive dark matter, and fuzzy dark matter. And I would like to refer to the talk that we heard yesterday about the possible. So now I don't have the wrong reference. I just put see yesterday's talk, then I solve my problem. Okay, Eleonora and I know what I'm talking about. So here there is this interaction between dark matter and massive neutrinos, which is given through this dimensionless quantity. So for people who are interested in what we did here, I give it in this sketch. We calculate through class the linear dark matter power spectrum. As initial conditions, we put it in Gauss form. We test the Helio mass functions through gadget, and then we just get the star formation and the metallicities from Gauss form. We put it in compass, and we find the BBH merge rate. So I'm going to see how, in the case that I have dark matter, what influence this is going to have in the merger rates of binary black holes. And the result it is here. So you can see that there is a difference. So now LIGO is there, here, this green part, but, which is the redshift. Huh? But as time goes on, and I expect, I don't know in whose generation, but whether any of us will be active at the time. Third generation interferometers will be there, then we will be able, to go to redshift above 6, and then we will be able to find a difference, and that means that gravitational waves may still say something about the origin, the microphysics of dark matter. It's called dark matter, it's dark matter what it is. So, so let me arrive to the concluding remarks. So indeed, people work with the lambda CDA model. We say that we have proved it, we have done a consistency check, we put it, we find it, and now we see that it has some problems. It is based on 2 unknown ingredients and a paradigm in search of a theory. So, my personal remark on that, historically the major breakthroughs in physics have been achieved when someone comes up with a theory based on simple premises of universal validity. As an example, Newton versus Ptolemy. The universality may later be in question, leading to further developments and new steps forward. Einstein and his theory. Now we need to take one more step. We accumulate more and more data, but we lack a satisfactory theory to accommodate them, and we are playing with models rather than theories. So my final remark is that science does not get along with make-dos like models, it needs theories. With that, thank you very much.
We're ready for questions.
Thank you for a very nice talk. I was intrigued, you mentioned some tests that could be done comparing by combination of LISA and LIGO, you mentioned maybe ground-based detectors without EM counterparts. Can you elaborate how that would work?
Yeah, I do not, because what I studied before was the case that I have a difference between the time I receive the gravitational wave and the time I receive the light. Okay?
Right, but that you would not, you said you don't need that.
I need that for some, but the ones that I said that I am going to have modification in the propagation, then I don't need an electromagnetic counterpart. Then if I have a modification in the propagation of gravitational waves, I see what kind of fingerprint they will leave in the waveform.
But
so
you say you don't need to be looking at the same source, you're saying. This is a statistical test. It's not...
this is, no, it could be, no, it could be one source. It can be transient.
But how could you possibly know that if you don't have an EM counterpart? The search regions are huge.
No, I know, but I know my source. I know where the gravitational wave.
No,
no. But if you have, we localize our sources.
No, not without an EM counterpart.
We do. Look, I can tell you it's very simple because look, when we say that we have electromagnetic counterparts, up to now, public 1. How did we localize the 9? We triangulate. What we need at least 3 interferometers to see the gravitational wave.
No, I don't mean to disagree with you, but they were, that one was particularly lucky, right? It was a very small search area, but most of the things are like...
No, but we know where they are. Don't laugh. If you take the third catalog of the collaboration, which is published, has 90 sources. You have the localization. That's why we have to localize it to go to say to our colleague who has the telescope, go to see there. So we localize the source.
I think the people like me looking for searching for counterparts would disagree about how easy it is to localize it.
But we do. But we do it. The localization. So that means that the localization of the 90 sources we have, we just do not accept it. That is correct. What do you imply by that?
You cannot pinpoint which galaxy it is. You can pinpoint a region of the sky which is bigger.
But what does this imply to what I'm saying? I don't need an electromagnetic counterpart. For me, it's localized good enough. Of course, I'm not going to tell you exactly, but I point to you the direction you have to go to see. For me, this localization is good enough, and what I take is the modification in the waveform. So the amplitude will change, and the phase will change. That's how I characterize it. So that's the way that we search for making a parameter estimation of how we do it. We have a bank of models that will depend on the parameters of my astrophysical object, and I map them with the detection.
Even the time work. I mean, imagine.
But that's the way that we work. So now.
No, but I'm saying the same source you see in LISA. How will you possibly see the same source in LIGO?
When I said there has nothing to do with LIGO, that was LISA. I said what LISA will be able to do, not LIGO. First thing, it was LISA, it was not LIGO. The second one, exactly with LISA and with 3G detectors, because LIGO cannot do it, we'll be able to have the same event at different times. So one can see the in-spiral, one will see the merger of the same event. So that's the whole idea, if you put it on the question.
Let's postpone the continuation for the break. Is there any other question?
You mentioned that exponential expansion could come from quantum gravity, yes?
I say that, to my mind, yes, the early stages of the expansion of the universe should not be treated within a classical theory, because they are at the regime where quantum gravity correction should not be neglected.
Okay. But couldn't it work the other way around? Could not quantum gravity change the causal structure so that there is no need for inflation anymore?
Well, what is okay, here is a semantics question. Yeah. Inflation, if we say inflation is the early stage of exponential expansion, okay, that's what we call inflation, then I'm saying up to now, in the 99.9% of the studies of inflation was done through a scalar field with a particular potential. So what I'm saying, this, it's the same thing. If you take Starobinsky inflation, if instead of having this R-squared term, you could map it. There are people who do supersymmetry or supergravity through mapping. So that's what I'm saying. Probably it's not a field with a tuned potential, but it's some correction in the action that comes from quantum gravity. That's all I'm saying.
But could not quantum gravity change the causal structure? So, because the need for inflation comes from the causal structure.
I don't understand what you call by causal structure.
So you say the need for inflation is that you say.
Inflation is what? Inflation, if you want, is some different dynamics from the dynamics that we have for the evolution of the universe, where the scale factor goes like time to, yeah, that's all. So these dynamics will become faster, will be different.
But why do you ask? Do we ask for it? We ask for it because this reason, this is more
because of these problems that people have, the horizon, the flatness, and things like that.
Yes, yes. But if you have a quantum space-time, this could change.
But at some point, your space-time should become classical.
But there might still be influence, and it might change. So
to change what? I don't know.
Change the geodesic. You can no longer. You would have deviation from how the geodesic are calculated, and then you have what we say it's classical connected might not be classical connected anymore due to corrections. So that's just only the idea.
I don't follow you very well.
We have to move on to the next one. I'm sorry, we don't have much more time. Thank you again for the nice talk.